So as a recap, remember we have talked through memory devices with SR latches and SR flip-flops. We've talked about D flip-flops. We've talked about how we're going to use those memory devices to combine our next state combinational logic and our feedback and our output combinational logic to make a finite state machine. So now we're going to actually do that and make the finite state machines. So remember this diagram. This was what we used for our SR latch when we were talking about our finite state machine version of that. So recall that a finite state machine has a finite number of states. The device, system, whatever, is going to be in one state at a time, and it moves from one state to another state via the transitions. The transitions are shown as arrows. The states, in this case, are shown as ovals. Sometimes we use squares. But the machine has to stay in a state until it receives the input that cause it to transition to the next state. So I mentioned this briefly before, but there's a couple different ways that we can do this. We can have a Mealy machine where the next state is dependent on the current state and the current inputs, and the output is also dependent on the current state and the current inputs, and that looks like this. So we've got our inputs, and our inputs feed into our, there's my pen, into our next state, and they feed into our output. We have that current state that's going to feed back. We've got our next state goes to our state, and our state goes to our output. Alternatively, we have a Moore machine. The Moore machine says that the next state depends on the current state and the current inputs, but the output depends only on the current state. So that looks like this. Notice that that feed forward path on the top is gone. So our input only goes into our next state. Our current state is still going to feed back to our next state. Our next state goes to our state goes to our output, and the output logic goes to the output. So a little bit simpler in the Moore machine. So which way do you go with these? Well, the Moore machine has less problems with the input glitches because your input glitches would affect the state, and then the state affects the output, and so your input glitches don't go directly to the output. So less prone to the glitches, but it also takes a little bit more time because things have to propagate all the way through the state to the output, and it may need additional logic, versus the Moore machine can be a little faster because it is responding directly to the inputs at times. I find that the Moore machine is easier to draw. So it sounds like a simple thing, but I find that the Moore machine is easier to draw. And when I say the draw, the state transition diagrams. So I will almost exclusively use the Moore machines in my examples. The Mealy machines, you can use them if you like, but I'm going to recommend the Moore machines just because they're simpler for a lot of the stuff we're going to do in our class. And I don't think that the reacting faster to inputs is a significant issue for most anything that we're doing in our class. And the reason for that is simply the difference in timing between the mechanical systems that we're going to deal with and the electronic control that we're going to deal with. So the computer systems are running quite fast. Even using the Arduino, it's still running quite fast relative to the mechanical systems that are going to be relatively slow. And so spending a few extra cycles does not strike me as a bad thing. It's really not going to make a huge difference. So we're going to look at a Moore machine example, and we're going to use a 2-bit counter. And so the way the 2-bit counter works is it's going to have a clock, which is going to cause it to count. And so it's just going to count up. So it's going to use 2 bits to count all the way up. And when it's done counting to its highest value, it's going to restart. So what are the inputs? Oh, I forgot to animate this. We'll walk through this real quick. So we've got our 2 bits are going to generate our outputs here. Well, this chip is ready to go with 4 bits, but we're only going to use 2 bits of them in our example. So you can see that the 4 output bits are all zeros, and then it goes 1, and then 3 zeros, and then it goes 0, 1, 0, 0, and 1, 1, 0, 0. So you can see it's counting in standard binary here. And so it's going to just keep counting up. Whoops. It's going to keep counting up, and then I stopped my animation, but you can see that it is going to get then to 0, 0, 0, 1, and it'll keep counting all the way to 1, 1, 1, 1, at which point it resets to 0, 0, 0, 0. We're only going to use 2 bits worth. We're gonna do the simpler version of it. And so we're going to define our inputs and our outputs and our states and all that. So our input is going to be the clock. Sometimes you call it count. clock, count, I don't care which one you use. Our states, we're only going to have 2 states, and our 2 states are going to be the same as our 2 outputs. This is a trivial output case, which is simpler. So our 2 states are going to be QA and QB. Just Q is typically our state, and so A and B. You could name them something else if you really want. Again, naming convention is not really a problem in this case. And so the idea is that we're going to count to the next value anytime that the count or clock is asserted. That's set to 1. And then stay there if it's a 0. And we're just going to keep counting up until we get to our maximum value, and then we'll reset. So as I mentioned, the outputs are trivial. What I mean is that the outputs are the same as the states, and so our output logic block is going to be nothing, basically. It's just going to pass through. So here's our state transition diagram. How many states do I need? Well, how many different outputs could I have? Well, 2 bits. I could have 4 different values, and so I'm going to, because my outputs can take 4 different values, I'm going to have 4 different states. So my input is count, my outputs are QA and QB, and so I'm going to take my 4 states, I'm going to label them S0, S1, S2, S3. I've arranged them in a square, and that's because I know what this is going to look like. You don't always know exactly what shape you should draw everything in, and so understand that there's some experience that goes into it, there's some iteration that goes into it, but generally if you got 4 states, drawing a square is a good start. So my 2 bits, my QA and my QB, they can take on, as I said, 4 different values. So the 4 different values are going to be 0, 0, 0, 1, 1, 0, and 1, 1. So I'm going to fill those in. Again, there's a bit of design here, and this is your choice as the designer, but I think it's simplest to label state S0 as the 0, 0 output case and state S3 as the 1, 1 output case. But if you wanted to shuffle the names and the output combinations, you could. It doesn't really make that much of a difference. What really matters is the output, not the naming. The naming is convenient for communicating it to another engineer. It doesn't really affect the functionality. So in this case, I've used circles. Sometimes we'll use ovals. Sometimes we'll use squares. But I have a shape that represents my state. The state is divided in half. It has a name, S0. It has outputs, 0, 0. So each state is associated with outputs. The transitions are not associated with outputs. The states are associated with outputs. And now I need to put in my arrows that are my transitions that move me from one state to another state, from one set of outputs to another set of outputs. So if count is 0, we know that we shouldn't do anything. And so we're going to stay in that state. If count is 1, we should move to the next state. So if we're in the state S0, we should move to state S1. If we're in state S1 and we get count 0, we stay there. We don't do anything. And if count is 1, we move to the next state, and so forth. This is just repeating. Anytime that count is 0, we stay put. Anytime count is 1, we advance. What happens when we are at the last state, S3? Well, we're going to reset our count. We're going to go from state S3 back to state S0. So we've drawn in our transitions. These move us among the states. The states have the outputs. Because this is a MRE machine, and the inputs don't affect the output directly. The only thing that directly affects the output is the state that you're in. So there is our state transition diagram. That's not too difficult. So we can write this out as saying that our next state, QA star and QB star, are functions of the count and the current states, QA and QB. And then we should be able to draw a next state truth table, sorry. And our next state truth table should take our count and our QA and our QB and give us our QA star and QB star. Oops, glitched again. So let's draw in some lines to differentiate some things. So these are my next states. So for these inputs, well, inputs and current states, we know that those are going to generate the next states, and they should also generate the outputs. So I'm going to combine all this into one big table, but the current states generate the outputs, and the combination of inputs and current states generates the next states. So notice again, inputs and current states go to the outputs. The outputs are not coming from the next states. So we should be able to fill this all in based on our diagram that we've drawn. Alternatively, we could do the tables first and then the diagrams. It doesn't really matter which way you go. They should have the same information. So here is the diagram we drew previously, just copied over. So if we've got our different combinations here written out, we've got all of our 0 cases, we've got all of our 1 cases for the count, we've got our QA and QB current states, then we ought to be able to do our next states. Notice that the states are defined a couple different ways. They're defined as a name, S0, S1, S2, S3, but they're also defined by a number, essentially. And that number in this case is the QA and the QB value. It gives a binary representation of the state. And that binary representation of the state is also the output, which is a little confusing, but you'll see some cases later where they're different. So anytime the count is 0, we know that QA and QB are the same as QA star and QB star, because there shouldn't be any change. We're staying in the same states. The fun only comes in when the count is 1. So when the count is 1, then we can start putting in our QA star and QB star as being different from our QA and QB. So this is where we're actually seeing the transitions. Notice in each of these cases that the output, QA and QB, are the same as the state, QA and QB, because they're tied together, and it's a trivial case. If you made this with a Mealy machine, you're going to need a separate output truth table that combines, again, the count, the QA and QB to generate the output. We're doing a Moore machine. It's a little simpler. So what are we going to do in terms of implementation? We've got our state transition diagram. We've got our next state and our output combinational logic truth tables. We could certainly go through and do all the wiring. So we need to look at what are the combinational logic gates needed in order to implement this. We're not going to actually implement the wiring. We're always going to do this in software, but it's worth seeing what's going to be necessary. So yeah, we're going to write it as combinational logic to start with for proving out how it works, and then we're going to go to code. For your midterm, which of course I'm sure that's what you care about because that's what you're going to be assessed on, the assessment is going to be on the code, not on the wiring and not on the combinational logic part. You should know how to do it, but I think functionally for what we're going to do in this class, you need to be able to do the state transition diagram, you need to be able to do the next state table, and you need to be able to write the code. But you should see how it works, even though I know you're not really going to do that ever in this class. Okay, so here's our Moore machine. We need memory, and we need next state logic, and we need output logic. So we're going to start with the memory. We've got 2 bits worth of output. We've got 2 bits worth of definition of state. And so because of that, we need 2 bits worth of memory. And the easiest choice for our memory, well, you know what it's going to be, but I'll show you on the next slide. We need next state logic, and I've already told you we're going to have 2 functions that are going to relate the count and the current state to the next state. And we need the output logic, and we know already that that's trivial, that the output is going to be a function of the current state, but we know that the output is going to be trivially just the current state. So you'll see that that's pretty simple. So the memory element, simplest memory element is going to be the D flip-flop. So the D flip-flop, we know that the next state, QA star, is going to be equal to D, the input, and you know, maybe we make that DA and DB just to remind ourselves that these are different inputs. And QB star is going to be DB. So the D is the simplest to implement, so that's the one I'm always going to go with. You could do it with others. We know you could do it with others, but the D makes everything easy. So let's write out our next state combinational logic. We have pre-filled in our table here. We don't need to worry right now about the output. We only need to care about the next state. So again, for these, this was the next state. So if count is 0, then we can fill in that block. And so that's 0, 0, 1, 1. If count is, oh, I suppose I should point out that this table, this entire table here, is for QA star. And this entire table, we'll do that in a different color. My stylus is still beeping at me about being low on battery. This entire table is for QB star. We've got different tables for the different states. So, and that's a confusing way to put it. When I say state, there's two different things that I'm talking about in terms of states. There's state, the circle that's labeled as S0, S1, and S2, and then there's also the binary representation of the states, and so maybe I should call these state bits. We've got two different tables for the two different state bits. That's a better way to put it. So QA star, I've got that first row there, and then if count is 1, I've got that next row, that 0, 1, 1, 0. But remember, notice this is a good case. I hadn't paid attention to this. Remember, this is gray code here. We had done this in our combinational logic, so that's gray code. And so because it's gray code, this was 0, 1, 1, 0, and this one gets reversed at the last two, so it's 0, 1, 0, 1, because we're using the gray code, because that's what we need in order to make this work for the K-maps. So for the QB star, same sort of thing. We're going to fill those in. I suppose my animations are in the other order. So for the QA star, writing out the equation, there's our things that we can combine, so we get an equation for QA star as a function of QA, count, and QB. For QB star, again, we're going to copy in our values from the table. We're going to group our adjacent ones, and we're going to write this out as our sum of products. So we've got an equation for each of these, for QA star and QB star. So that is our next state combinational logic, ready to go. And when we start putting these together, we've got our next state combinational logic. So we need our count coming in as an input. We need our memory elements. So remember, we talked about these memory elements. We got our two D flip-flops there. And we're going to feed those back so that we've got QA, QB, not QA, not QB available as inputs to our next state logic. So that's the feedback. And now we can start building up our logic for our next state here. So QA star is going to be based on QA and not count. It's going to have QA and not QB. It's going to have not QA and QB and count. QB star is going to be QB and not count and not QB. And then we're going to OR those together and to get QA star and QB star, and those feed into our memory elements, so we're going to hold those values. And then we also have our clock. Remember, all this has got to be synchronous, so we're going to have a clock signal going there. And then those two things coming off of there are the QA and QB. That is what I'm talking about in terms of trivial. That is going directly to the output. That is the output. So those are the two bits that make up the state definition, and they're also the two bits that make up the output. So that block right there is the next state logic. That block is the memory, and that block is the output logic. The output logic is trivial. There's nothing going on. But it has all the elements that we're looking for. It's got next state, it's got state, memory, and it's got output logic. So that's what we should see every time. Okay. So what if we used a 4-bit up-down counter? This is the 74169. It's a standard chip you can buy. What does it have in it? Well, let's see. We've got our... Where's my animations? There we go. There's our inputs. There is our next state logic. Doesn't look the same as what we're dealing with, but it's pretty close. There's our memory. And there's the output. Notice that their outputs, they used inverters, so they're used a slightly different logic scheme, but it's still basically the same thing. They've got inputs, next state logic, memory, and outputs. Same as we're dealing with. So you could design this system in the same way. I don't think you'd want to. You can just buy this IC, but you certainly could. So what do we use state machines for? Well, there's lots of different applications. Remember that these are a way to define moving through states where each state has a particular behavior associated with it. And this is what I called supervisory control. So you can talk about robot positioning. If you've got an object seeking or a position control, as long as what you're talking about is going to be purely binary, you're going to be talking about on-off sorts of things, which does work in a lot of cases, you can do robot control. You can do selection of gains in a gain schedule controller or a hybrid controller. I've seen mentions of using them for artificial intelligence. So if you're into video games and you want to have decision making for non-player characters, certainly that's an option. I also see reactive agents, biologically inspired reactive agents, swarm behavior, often defined using ants. You can do that all with state machines. And then I also saw a good example of biological modeling with T-cell activation. So I'll show you a couple of quick examples of these. So here's an artificial intelligence example. So in this case, talking about ants. I don't know why they use ants, but ants are a common task for this. I took this from a CS course. So you can see that this ant, it's going to start here. That's what this circle is where this starts. So the state machine starts by going to the forage state. Now these states are a little more general, I think, than the ones that we're going to deal with. We're going to deal with things that are going to be like motor on, motor off. But these are a little broader, so it's a foraging state. And then notice what happens is it has these transitions. There's an input. Well, there's a vision seeing a larger creature, and so that goes to the run state, and if it has escaped, it's figured out that it's safe again, it goes back to foraging. So again, it's in a state, it's doing something. When it has a transition due to some sort of input combination, it moves to a new state, and that new state says, run away. If it's foraging, it might move to food, and then if it sees something, it runs away. If it has food, it might, if it has food and it's picked up the food, it might move to the nest and then go back to foraging. And so you can write out a lot of this sort of logic as a state machine. You can do the same sort of thing, excuse me, with NPC behavior in video games. Again, the same sort of thing. You're looking at inputs, often coming from a user, possibly coming from other processes in the game world, and then making some sort of action. I like this one. This one comes from a biological system. So I didn't write down the paper number, unfortunately. So the T cell is part of your immune system, and so you've got these dendritic cells that wait at the human environment interface, and they grab samples of environmental stuff. So you're breathing something in, and it grabs a sample of it, it gives it to the T cell. The T cell does some sort of process with the sample, and then if it's got a problem, it activates the immune response. Well, so how does it do that? It's basically a state machine. So you start at the empty state, there's no sample. When a sample arrives, you move to the occupied state. And then if it's reacting with this in a particular way, it moves to the partial activation state. If it continues reacting, it goes to the full activation state. If it got partially activated but then didn't go any further, it rejects it and moves on. And the full activation state is when you have an immune response. Now, interesting thing about these is that the cases here are marked as being duration of binding. So how long does it bind is the input. And this is a probabilistic thing. It is not a deterministic system in the same way that the things we're dealing with. So there's lots of different ways you can use these. We're going to use them for robots, but certainly there's other ways you can use them in the rest of your life. So how do we go about designing them? Well, that's always the catch. So we've talked a little bit about how we write the state transition diagrams, the state transition tables, the next state tables, and the output tables. So what do we do? Well, this is a design problem. This is a design problem in the same sense that you have a mechanical design problem in another class. So it's very much going to follow the same sort of process that you would think of anywhere else. You're going to start by abstracting the problem. You're going to specify the inputs and the outputs and what you want to have happen, essentially your performance requirements. You are going to then use that to create your finite state machine. When you have your finite state machine, you'll do some iteration through state minimization. The state assignment is the binary code. So this is where you get from taking your design and implementing it. Well, you're going to assign the binary codes, and then when you've got the binary codes, that tells you how many flip-flops you need, and when you know how many flip-flops you need, then you can start writing out your next state logic. And then once you've got your next state logic and your output logic, you can then select individual gates or select an implementation platform, and you can put it together, and then you can always simulate and implement it. So the first part here is very much your design. The next part, we've got some iteration, and then we've got some implementation and testing. So very similar to a mechanical design process. If, however, you're doing software implementation instead of hardware implementation, then a lot of that stuff falls out. And so we're going to skip a lot of it in terms of stuff we do in class. We are definitely going to still do the tables. We are definitely still going to think about the minimization, and we're always going to test. But we don't necessarily need We can flip back here. We don't necessarily need to do the state assignment and the flip-flops and the next state logic in the same sense, because if we're not implementing with hardware, then a lot of that stuff is just taken care of by our compiler. So let's do an example, and let's use a door lock again. So we're going to use a 2-button door lock, only this one's not going to be nearly as bad as the last one. So we've got 2 buttons, B1 and B2, and the result is lock. And in this case, we want to have the order matter. So previously we had a static system and we had to press things all at the same time, and now we want a dynamic system where the unlock is going to be press and release 2 and then press and release 1. So the order matters and the timing matters a little bit. So here is a particular execution diagram. So you can see that we've pressed and released 1, we've pressed and released 2, we've pressed and released 2, we've pressed and released 1, and so finally here we press and release 2 and then press and release 1. So that is the one that should trigger it to unlock, and sure enough, in our lock it goes high at that point. Now, we didn't specify this, but it goes high for a little bit and then it goes low again, so it does relock itself. So that is the case that's going to work for us. Pressing and releasing and pressing and releasing simultaneously does not work. It has to be a press and release and then a press and release. So we need to understand what's going on. We need to make our abstract representation. So let's go through these steps. So what are the inputs? The inputs are going to be B1 and B2. They are asynchronous, but we will synchronize them for implementation. We know that our output is L, is the lock case. So it is either 0 for locked or 1 for unlocked. Excuse me. And so when we think about what's going to happen, we're going to press and release and press and release. And at that point, it should go unlocked. And so we're going to end up with 5 different states. Idle, and then B2 is pressed, and then B2 is released, and B1 is pressed, and B1 is released. And at that point, everything unlocks. So we can start drawing in our cases here. So the ideal is that we're going to get a 0-1 case, which is B2 is pressed and B1 is not pressed, and then 0-0, and then a 1-0, and then a 0-0. And at that point, we unlock. I forgot to mention that these outputs here, it is always locked until you get to that last state, and then it's unlocked, which I said that in terms of words, but remember that's going to be a bunch of zeros and then 1 in the unlock, or in the output. So what happens if you're sitting at idle and you don't get a 0-1? Well, then it's going to stay in its spot. So if I've not drawn in any sort of transitions, there's nothing written over here. It's assumed to be everything that is not written in elsewhere. So when you're doing this in your own projects, I'm going to tell you that that's the assumption, but it is good practice for you, especially the first couple times you do this, to write in every possible input combination. So instead of leaving it blank and saying, well, it's everything else, let's actually write it in. So 0, 0, 0, 1 is the one we want. So 1, 0, 1, 1. Any of those 3 combinations keeps us there. So if we get to B2 being pressed, and you just keep pressing B2. So you press the B2 and you just keep holding it. Well, you should stay in the B2 press state. There's no reason to move anywhere, which is why we've got this loop here with the 0-1 case. We just hang out there until something changes. Same thing for the others. If you press B2 and release it and then you just don't do anything, we can stay in that state. Is that a good behavior? Not really. We should probably have a timeout case for this, but we're not including that. This is a very simple case. You can certainly add complexity as you go. What happens if you get anything other than the appropriate next state or next input combination? You should go back to the idle state. So again, I've drawn these in as having no text. I think that that is understood to be correct, but for your purposes as a learner, as your purpose for practicing, please don't do this. Let's write them all out. So if we are at this S1 and we get a 0-0, we move on to the S2. If we get a 0-1, we stay put. But what happens if we get a 1-0 or a 1-1? Well, in that case, we should go back to idle. Same sort of thing for B2, B1 being pressed, B1 being released. Write them all in. This last one here, what happens on this transition? Again, this is not a great design. We should probably hang out in the unlock case for a little bit. There should be some sort of timer, but in this case, to make it simple, it's just automatically it's going to unlock and automatically go back to idle. So there's my note. An arrow without a specific input value implies anything else is not implied. That's not identified elsewhere. This gets to be a problem. The reason it gets to be a problem is that students often forget that some of the things that they have marked as not possible get lumped in there. So if you had, let's say you could not physically press the two buttons at the same time, so the 1-1 case was excluded. Well, if I write it in as an arrow with nothing else, then the 1-1 case is implied to be in that arrow, and so if somehow it breaks in the 1-1 case there, it goes through. So there's a lot of there's a lot of potential for debugging problems when you start doing the arrows without writing in everything else. The other fun thing is if you write in the arrows with all possible combinations, instead of leaving them blank, what you'll see real quick here is that, let's look at this state S1. I've got 0, 0, 0, 1, 1, 0, 1, 1. I've got 4 different input combinations, which makes sense because I've got 2 inputs. They've each got 2 possible cases. So I've got 4 combinations, and so all 4 combinations are represented. I haven't missed any. I haven't duplicated any. Everything's there. If I start going with implied, sometimes, I start duplicating or I start omitting things. It'll also show up in your code when you start using else statements. When you start using an else, bad things happen, and you'll see it in your labs. Okay, so I'm going to skip state minimization. That's a whole nother video. So state assignment. Well, how many states do I have, and then how many bits do I need in order to represent those, and then what are my different schemes for representing them? Well, how many bits do I need in this particular case? I've got 5 different states, and so 5 different states is going to require 3 bits. Well, a little bit less than 3 bits, but I can't do, partial bits, so I'm going to use 3 bits. So I could use a traditional binary sequence, I could use a gray code sequence, or this one-hot sequence. So the one-hot sequence says I'm going to have 1 bit for every state that I want. It requires a little bit more hardware, but it's very easy to deal with. It's really up to you. It's a design problem. You can choose whichever one you want. So in this particular case, like I said, n is 5, so we need log base 2 of 5, which is 3 bits. So if we use gray code, then we're going to have states S0 through S4. And then, so if I write this out in gray code, there are some combinations of Q1, Q2, Q3. And so Q1, Q2, Q3 are the bits that make up my state representations. So each of my states has a name and a bit combination, and then the bit combination is what I'm going to need for implementation. I will always choose a D flip-flop because it makes everything easy. So my next states are going to be Q1 star, Q2 star, Q3 star, which are going to be functions of my inputs, B1, B2, and my current states, Q1, Q2, Q3. And my output, L, is going to be a function, because I'm choosing a more machine, of Q1, Q2, and Q3. So I know what the form of this is going to be, but I still need to actually write out my tables and then derive my equations. So my next state table, that one, if I know my, well, I suppose I should point out, this is a little different than the previous table that I did. There's lots of different ways to do this one. This one is going to be written out in terms of the state names, and then we can also do the one on the right, which is written out in terms of the state bits. So they both tell you the same information, and you'll see that, but they are slightly different. So the next state table in terms of the names is on the left. So if I'm in state 0, and I get a 0, 1, I move to state S1. Otherwise, I stay in S0. If I'm in state S1 and I get the correct input, 0, 0, I move to state S2. If I get the same input that got me there, I stay in S1. Otherwise, I go back to idle. And we can just fill these in. State 2 will move to state 3, or stay in state 2, or go back to idle. State 3 will move to 4, or stay in 3, or go back to idle. And 4 will stay in 4, or go back to idle. And again, that's really a design decision. You could fix it if you wanted, but this is a real simple case. The same information shows up on this other table. Remember, I'm going to draw in my lines here. So I've got my input and current states. I've got my next states. And then I've also got my output. There we go. My input and my current states give me my next states. My current states also give me my output. So same sort of information. Notice that entire block there that's shaded in is state S0. All the Q1, Q2, Q3, they're all zeros throughout the entire thing. That whole thing is defined as state S0. So I know that if I get a 0, 1 on my input is when I should change to the next state. That's the 0, 0, 1 on my bits there. Alternatively, it goes back to idle, 0, 0, 0. The next block is S1, so you can see it's got the same information. It's just a different representation. So in this case, I'm going to either get a 0, 0 input on my B1 and B2, which takes me to the next state, S2, or I'm going to stay in S1, or I'm going to go back to idle. Same thing for S2. I'm just going to flip through these. You can see the same information. There we go. So it's a more complex way to say it, but it's the same information as on the smaller table. And then we know that the only time that we unlock is when we're in state S4. So there we go. State S4, regardless of the input combination, gives me unlocked. So we've got our next state table in the bottom left. We've got our larger next state and output table on the right. So we should be able to use these then to make our K-maps. And if we can make our K-maps, then we can write out our next state logic as a combinational logic equation. So there's more inputs in this case, so we have to get a little fancier. So now we're going to have our Q1 star, our next state, our next Q1 state, is going to be split into two tables when Q1 is 0 versus when Q1 is 1, and so you can picture these as being stacked one on top of the other. And we're going to have B1 and B2 on one side and Q2 and Q3 on the other side. So you can fill all these in. These values are taken directly from the previous table, which is why we write out those tables. So these are taken directly from the previous tables. Notice that this one, on the right-hand side, Q2, Q3, there's a lot of X's going in there. Why are there a lot of X's? Well, remember that we had 3 bits, but we didn't need all possible combinations of the 3 bits. And so because of that, we have a bunch of combinations of those that are simply not used. And because they're not used, we're going to put them in as don't cares, the X's. So the don't cares make it a little more convenient to make combinations of adjacent ones for writing out our equations. So in this case, we're just going to picture these as being stacked one on top of the other, and so we're going to join those adjacent ones as being stacked on top of each other. And so Q1 star is now a function of Q2, Q3, B1, B2. If you don't remember how to do this, go back to the combinational logic section and do it a couple more times. So we can do the same thing with Q2 star. Again, these are stacked one on top of the other. Again, we're going to end up with a lot of X's and don't cares in there because these are combinations of Q1 and Q3 that are simply not used because we didn't use all of the 3-bit combinations. So that's why those are in there. So again, I'm going to copy in the values from the previous table. So you can see my 1s and my 0s. I'm looking for my adjacent 1s. So there's a grouping of adjacent 1s. There's another grouping of adjacent 1s that includes a don't care, which makes it kind of convenient. And remember, these are stacked one on top of the other. So now these circled ones are stacked one on top of the other and adjacent that way. So now my Q2 star is a little more complicated. We got those 3 different groupings. And we can do the same thing for Q3 star. So for Q3 star, I'm going to have a couple different groupings here. And alternatively, I could simplify that second one, the purple pair, by doing the red grouping of 4 because I can include those don't cares. It makes it a little bit simpler. My output logic, well, the output logic is pretty easy because I know that the output logic only happens in state S4, and so I know the combination of Q1, Q2, not Q3 gives me that. So that's my output logic. So putting it all together, here is my next state logic, here's my output logic, and so I should be able to then make myself a schematic using these logic implementations. So here it is. Notice that I've got my synchronizers at the beginning. Those are the D flip-flops. I've got my clock. Then I've got, there we go. There's my synchronizers. There's my next state logic. There's my memory. And there's my output logic. So it's all the same elements as before. It's just building up the stuff that we have written out as equations, and we're just building it up as a wiring diagram. So what happens when we run this with our timing diagram here? So we've got our clock signal. Whoops, I forgot this was not animated. Okay, so we've got our clock signal going on. Notice that B2 goes, B1 goes, and so these have to be synchronized. And so it aligns with the next clock signal, and this one changes and it's aligned with the next rising edge. This is all rising edge synchronized. This one aligns with the next clock signal. This one aligns with the next clock signal. So they're shifted a little bit in time based on the synchronization, not the end of the world. But when these go through the right sequence, then we get to finally Q1 and Q2 and not Q3, and it unlocks, which is what we expected to see. So thinking ahead, are there any ways that this could go wrong? Yes, there are, and you'll see that in the next video. But for now, in a perfect case, it works well. But how would you do this if you were writing this out in Arduino code? Well, it's a little different. Obviously, we're not going to build up all these gates. So I've given you some sample code here, and there's some sample code provided with the labs as well. So this is a really terrible example in the Arduino code, but it gives you the same idea of how this might work. So this is for 2 states. So I might start by naming my states. Now, there are other ways to do this. I tend to use the define here to define S0 and S1. Those are my names, and I give them a code, and the codes just need to be unique numbers that are sufficiently large that they're not going to be a problem, so I've called them 100 and 101. I assign my input pins, so there's got to be some sort of inputs that are going to drive all this, so I've got pin input A and input B. I've got my output pins. In this case, I've only got 1. And then I've got my state, my current state. And my current state, I'm going to assume, is going to be starting from S0. It wasn't really defined in the diagram, but I'm going to assume we're going to start from S0. And then remember, I've got my pins for my inputs, but I also have the values of those inputs. So that's in A and in B. So I'm going to start by declaring my output as an output, and I'm going to digital write low because I'm starting in S0. So within my loop, I'm going to read the pins and store the values. This is something that often gets confused in student labs. You need to make sure that you're reading the pins and storing the values to a variable that is set to store the values. I often see those reversed for some reason in code that students produce the first time, and it never works, obviously. So here's the key for the Arduino implementation. This is how I want you to implement it. I understand that this is not the best way in terms of clock cycles. I understand that this is not the most efficient way to do things. This is, however, a very easy way to do things that makes it easy to debug. So please, please, please follow the way that I've written it. We're going to use a switch case. We're going to switch based on the current state. We're going to have cases that represent each of our states. So case S0, well, that's going to be my state 0. It's going to have an output. Oh, look, my state has an output. It's going to check the inputs, and then based on the inputs, switch to the next state. So check the inputs, and then based on each of the transitions will be an if case, and then the next state is going to be dependent on what the transition value is, and then you end with a break. Same thing for case S0, that's case S1, that's my state S1. So you're going to see some more of this. That's the quick rundown, but you're going to see some more of this. I have some examples, and I have a video on state reduction that are coming up. So this was a long one. Sorry, it's a lot of stuff crammed in there. Yeah, we'll pick it up with reduction, state reduction, and examples